So the first video from chapter 8 is going to be on energy and kinetic energy, and it's going to cover chapters 8-1 and 8-2. Okay, so where we're headed with this. So chapter 8, we're going to start an entirely different approach to mechanics. So up to this point, we've been looking at Newtonian mechanics, right? And as you know, Newtonian mechanics is based on forces, right? It all hinges on, well, Newton's laws, in particular Newton's second law that says the net force is the mass times the acceleration. So it's all based on forces. Now, forces, as you're well aware, are vectors, which have a direction, which generally means that vectors are just harder to deal with. And in fact, in certain situations, vectors can be really, really hard, and Newtonian mechanics can be really hard. So sort of a classic example is, imagine if you have a trough, and you've got a ball rolling up and down the sides of a trough. So the Newtonian approach is actually, that problem is incredibly difficult, because if you think about it, there's going to be a normal force, but the direction of the normal force is actually going to be changing all the time, and that's just hard to deal with. So the next several chapters we're going to be looking at an alternative approach, and this is the conservation approach. And the whole idea behind the conservation approach is to exploit certain quantities that are conserved. And in physics, to be conserved means that they stay constant. So you look at a system, a collection of particles, and you look at things that stay the same. So, and just one point to note, though, is that this conservation approach is not going to replace Newtonian mechanics. So there are some questions that the conservation approach can't answer. So we will still need to go back to forces at some point. Okay, so first off, we're going to look at energy. So energy describes the state of a particle, an object, or a system. So, and state here means that it includes the motion of a particle, so how it's moving, and its configuration. So imagine if you've got a box with a bunch of particles in it. So the configuration basically just means where the particles exactly are. So the location of things. So the nice thing about energy is that energy is a scalar value, and as you've probably figured out by now, scalars are much easier to deal with than vectors. So so generally speaking, energy is just going to be an easier way to do things than forces. Although keep in mind, this conservation of energy idea isn't going to allow us to do everything. So, and we'll get to how you calculate energy in a minute, but just to put it on here, so the SI unit for energy is something called the joule, named after yet another dead white guy, so James Prescott Joule. Abbreviation is capital J, and a joule is a kilogram times a meter per second squared, or also a Newton times a meter. Okay, so last thing in this video, so kinetic energy. So kinetic energy, we're going to use a K to stand for kinetic energy, and it's the energy of a moving object. So if you have a single particle that's moving, you can calculate its kinetic energy K as a half times the mass times the speed squared. Now, and if you have a whole bunch of particles in your system, well, to get the total kinetic energy, you just add up all the individual kinetic energies. So the total kinetic energy of the system is just the sum, where I is just denoting all the different particles. So if you have 10 particles in your system, you go from 1 to 10, and for each of the particle, you take a half times the particle's mass times its speed, and you just add all those up.